Hello, my name is Ekaterina Khamtsova, and in this video, I would like to present you a paper entitled Convolutional Persistence as a Remedy to Neuromodel Analysis. This is a joint work with Guido Zuccon, Xi Wang, and Maza Bakhtasmoglu, and it is presented in the 26th International Conference on Artificial Intelligence and Statistics. It is well known that deep neural networks are extremely efficient learning systems. However, they are hard to analyze due to high dimensionality of the weight space. The goal of this work is to analyze the weight distribution of filters or kernels of convolutional layers. In particular, we studied the topology of the space populated by convolutional filters. The main outcome of this work is that we have found a correlation between some persistent topological features and some properties of the network, in particular model generalizability. The main two applications that we consider in this work are model selection and model behavior analysis. We propose a measure that we called convolutional topology representation, or ConvTop-Rep, as a meaningful and compact representation of the topology of convolutional layers. We show that it is indicative of model generalizability and can be used as a competitive model selection criterion in the context of domain generalization. Moreover, it provides valuable insights into the behavior of the model. Here is the pipeline of calculating our measure for one channel. So we start with the set of filters and project them to a Euclidean manifold where the distance between filters is defined as Euclidean distance. Then we construct a Vietoris-Rips complex on this set of filters. Finally, we apply persistent homology by gradually increasing the threshold epsilon and monitoring the creation and destruction of first-dimensional topological features, or holes. The resulting persistence diagram is summarized as a first Wasserstein distance of the points to the diagonal. Let me give you an example that would help visualizing the meaning of our measure. Assume that our convolutional layer only consists of 4 kernels. Each of them has a dimensionality 2 by 2, as shown in the picture. Assume also that they only black and white. One is completely white and one is completely black, and 2 others have white row columns and black columns. We first calculate a pairwise distance matrix between these filters and use it as a metric space to build a Vietoris-Rips complex, where each simplex corresponds to a subset of points with a threshold smaller or equal than epsilon. So we start with only 4 simplices, each corresponding to a filter. And then we start increasing the threshold. And once the threshold reaches square root of 2, which is the smallest distance between our filters, the new simplices are added to the complex. And we continue doing this and increase the threshold even further. At the threshold of epsilon equals 2, tetrahedron is filled into this space. And then after that, the topology of the space does not change anymore. So this is a filtration associated to this metric space. And what we do is we look at this filtration and monitor the creation and the destruction of different topological features. In this work, we look at 0-dimensional and first-dimensional features, namely connected components and holes. So let's start with the connected components. In the beginning, we have 4 connected components. Then at the threshold of square root of 2, 3 of these connected components disappear as they're being merged into one connected component. That persisted until the end of the filtration. The summary of this evolution of topology is summarized in the persistence diagram, where each point represents the birth and the death of a persistent feature. So as we can see here, we have 3 features that appeared at scale 0 and disappeared at scale square root of 2, which correspond to these 3 points in the persistence diagram. So these 3 orange points in the persistence diagram. Another topological features that appeared only at scale square root of 2 is a hole. As you can see in here, we can clearly see a hole that persisted until it disappeared at scale 2, and this corresponds to this point. So first dimensional, so the distance between this point to the diagonal represents the lifespan of the hole. So it gives us an information about the distribution of their filters in space with respect to each other. The main contribution of this paper is that we found that the smaller is the lifespan of these holes and the fewer the holes are, the better is the model, the more generalizable is the model. So when we calculate this for all the channels of the layer and then sum the lifespans for all the holes if there are many holes. And this is the representation of the topology of this layer. And we say that the smaller is the total lifespan of all the holes, the better is the network. So the smaller is the conftop rep measure, the better is the network. Here is another example, slightly modified example from the previous case, where instead of black and white columns here, we take different shades of gray. So obviously the distance matrix changed and the space of filters has changed. And we can see that now there are no holes generated by this filtration. We only have connected components that gradually disappear at different scales. So let's take a look at what happens with the persistence diagram throughout training. In the very beginning, so these are the diagrams in the beginning, in the middle, and in the end of the training for one of the setups that we have used. In the beginning, the filters are initialized around 0. And as the training progresses, these points go upwards. So the birth of both zero-dimensional, first-dimensional features increases, as you can see from this diagram. So this is because the norm of the filters increase. However, we can see that the points, the blue points that represent holes, the lifespan of holes, they remain close to the diagonal, meaning that there is no one hole that persisted for a long time throughout the filtration. The first application of our approach is a model selection in the context of domain generalization. In domain generalization, we have a source data set that was seen during training, and we have unlabeled target data sets, and we would like to select the best model, trained model, for target data sets. Apart from a normal training, we also considered several training strategies, namely random convolution and YADA. Random convolutions augments the source data set by applying convolutional filters with random parameters. And YADA extends the source data set with adversarial samples generated by maximizing the entropy of the latent representation of the network. So we transform the model selection problem into not only selecting the best model, but also selecting the best training strategy for each data set. And we have seen that for different experimental setups, so different training strategies perform better. So for example, for DGIS data set, for the first setup, the best strategy is random convolutions, while for CIFAR, the best strategy is YADA. Here are the results of model selection comparison. We use other baselines from domain generalization model selection as a comparison. The first 4 methods are activation-based. The last 2 methods are weight-based. One might ask, why do we need topology at all? Why don't we just take the weight of the norm of the weights and consider just a much simpler approach, weight-based approach. And we show that this approach doesn't actually perform very well, and it's significantly worse. In fact, it gives the worst performance on our last experimental setup. Moreover, and neural persistence is another topology-based, weight-based method, but instead of looking at convolutional layers, the authors look at fully connected layers and extract some topological properties from that layer. And we show that while it performs relatively well, quite well on digits setup, it does not perform very well on the second setup, where the network is deeper and we have much more convolutional layers and only one fully connected layer in the end of the network. Know that across all the experimental setups, our method gives competitive performance, outperforming other baselines. The second application of our approach is the model analysis. In here, we look at the evolution of conf-top-rep throughout training and look at the effect of each training strategies on different parts of the network. In particular, we look to the left, we have the first layers, and the right plot represents the last layers of the network. And we see that in both cases, during training, conf-top-rep continuously decreases. However, the smallest values for the first layers seem to have a random convolution training strategy. It is also consistent with the knowledge of our knowledge of random convolution. As we know, the authors propose to add different, augment the data set by adding different textual variations to the data set, and therefore they primarily affect the first layers of the network, while MIADA generates adversarial samples based on the output of the network, and therefore it more affects the last layers of the network, which is reflected in the plot of conf-top-rep. In addition, we can even see different steps of MIADA algorithm. In the very beginning, the evolution of conf-top-rep is almost identical for MIADA and ERM, which is correct because in the first 10 epochs, they are identical. However, after epoch 10, the first round of adversarial samples have been generated, and we can clearly see a sudden drop in conf-top-rep, followed by another drop after epoch 18, where the second round of adversarial generation happens from MIADA. So with our method, with our measure, we can look at the effect of each training strategy or strategies on different parts of the network. And the last application that I would like to show is the use of our measure for as a criteria for early stopping. It is known that random convolution introduces variations to the dataset. However, the dataset doesn't converge to a certain point because the augmentation is continuous. So, and there is infinite number of possible augmentations. Therefore, it is not clear on when we should stop when we train with random convolution. In this example, I show that if we just look at the validation loss, we are supposed to stop at around epoch 30, after which it seems to be overfeeding on the source data. However, the target performance does not support this claim, and in fact, we see that if we continue training further, we can have significant gains in target performance. With our method, we can detect this behavior. We see that conf-top-rep continues to decreasing, and after some point, it stops changing significantly. So the weights continue changing. However, the topology of the space does not change, which we can use as a way to define the early stopping. In the paper, we discuss a bit more in details the advantages of disadvantages of using conf-top-rep for early stopping criteria, as an early stopping criteria. Thank you very much for your attention. You may contact me at this email, and the code is publicly available as well. Please check it out if you're interested, and please don't hesitate to ask any questions. Thank you very much, and I'm looking forward to see you in the conference.